It is time to start. We're a couple people short. It's supposed to be 13, 2, 5, 7, 9. Yeah, it's supposed to be 4 more people than what I'm looking at, but well, maybe that's where this thing comes in. When it's a smaller group like this, it's kind of nice to hold the class here in the lab rather than in a classroom like we did last fall for, a couple of reasons. If I want to demonstrate what I'm talking about with some sort of equipment, it's all just sitting right there where I can grab it, and that's handy. Or if one of you wants to borrow a calculator during a quiz, they're right there. Yeah.
Or the fact that our lab is right here.
Yeah, saves you changing rooms on Friday. The possible downside is that recording the lectures, everything was hardwired in up there in, oh, I think I see some familiar faces through the window. I'll just pause for a moment while they come in. Grab one from each of the 4 piles as you go by here. Wow. Well, yeah, but it wasn't like that every day. So anyhow, the downside of meeting in this room instead of a classroom is that recording the lectures, this laptop is connected to our network wirelessly. And if the network gets busy, well, we'll see what happens. I've tried it out a couple of times and it seems to work all right. Once or twice, the picture started to break up a little down in the corner. So it makes me just a little nervous. But that was just recording for a minute or two. So we'll see what happens recording whole classes. And if there's a problem, we'll just move to a classroom like we had in the fall. But if we can get away with it, it's kind of nice to be in here. I should at least briefly go over a few high points from the syllabus. For those of you who took Physics 131 from me last fall, it's the same thing, okay? You can just go to sleep for the next couple of minutes because it's going to be just as if you weren't even gone. We're just going to keep on going with what amounts to, well, it's not the same course because the subject matter is a little different, but it's organized the same way. 3 exams and a quiz every week on the homework. But there are a couple of people who weren't here for 131, so I should probably explain that, well, the grading system is on the bottom of the first page of the syllabus there. Quizzes, labs, exams, and so on. The quizzes are quizzes on the homework. I do not collect homework in the sense of telling you, hand in your homework, and I sit there and grade it, because half of the homework I'd be grading was probably something that somebody copied off of their friend anyhow. What I like to do instead is quiz you on the homework. I collect it out of your head instead of off of a piece of paper. So the homework for this course, homework for just about all of my courses, is written out on handouts instead of being in the textbook, which reminds me, I got an email reminding me the other day that a copy of the textbook is on reserve at the circulation desk in the library. It's one of these things where you can only keep it for, I don't know, an hour or something like that, and you can't take it home with you, but that would be sort of another reason to maybe, you don't actually have to buy the textbook. What I usually suggest actually, because I did once have a student tell me after he'd left and gone on to, I think he went to the University of Rochester, and he said, I never used that book when I was taking your course, but now I use it all the time because this course was a prerequisite for other things he was taking, and he wanted to use the textbook as a reference. So you might want it for that. I suggest getting an older edition off of eBay for $15 or $20 rather than paying 10 times that much for a brand new. The older editions They contain all the same stuff. It's just been shuffled around a little differently so that they can try and make you buy a new book. But anyhow, rather than assigning end of chapter problems out of the textbook, which they're changing on me every 3 years when they come out with new editions, the first 4 assignments are written out in this same handout, the syllabus. The first 5 pages of the syllabus are all the things that are supposed to be in a syllabus, like the course description and the grading system and so on. Starting on page 6, there are a few homework assignments. The rest of them will be in another handout that I'll give you in a few weeks. But it says there on page 6, section 1, electric and gravitational fields. And it says refers to some parts of the textbook. That's telling you which part of the current edition of the textbook corresponds to what I'll be going over. And then it says quiz A and there's a question, and it says quiz B and there's a question, and so on. Quiz F has 3 questions. One of those 6 quizzes will be chosen, well, actually already has been chosen at random. I changed the numbers so that the answers come out different. Otherwise, it's the same problem you've worked on for homework. The answers are given right underneath the questions, but sometimes you need a little explanation of how to get the answers. For that, notice at just about the 2nd or 3rd line from the top of page 6, there's a website written there. Let me emphasize that I am not using Blackboard except for the videos. You want to watch the video, that'll be in Blackboard. For everything else, the solutions to the homework, or for that matter, if you can't find your formula sheet when you want to work on your homework and it's a Saturday night, so well, let's make it more realistic. A Sunday night so that you can't come and ask me for another copy. The lab book, everything is in the website. This one on the faculty server, it's written there at the top of page 6. You get stuck, you can look at that to see how I did the problem and get yourself unstuck, okay? So one of these 6 quizzes will be waiting for you. I would be saying a week from today, except a week from today is a holiday. College will be closed and it's Martin Luther King Day. So instead of the usual 7 days from now, it will be 9 days from now, a week from Wednesday. One of those 6 quizzes, with the numbers changed, will be the first 15 or 20 minutes of the class. And you'll need to do it and hand it in, and then I'll go over it. And so anyhow, that's how the homework and the quizzes work. Roughly once a month, there's an exam, which, unlike the quizzes, are not just recycled homework questions. There's also a final exam at the end of the course. It covers the entire course. There's a lab every week, 10 points each. Your grade for the course is just add them all up. No elaborate weighted averaging or anything like that. Just a point is a point no matter where it comes from. So that's part of how I've got the course organized anyhow. In any course, you should read through the syllabus because it's the rules of the game. And there are things that I haven't mentioned in the 9 minutes I've been talking about it here. But that tells you what you need to do to get started anyhow. Sometime in the next 9 days, get so you can do those half a dozen quizzes that are in that handout there. And you can do it at home. You can do the same thing when you get here. As far as the rest of these piles of paper, this one is the lab book. That's the directions for all of the labs we're going to do in this course. This one is the formula sheet, your faithful friend and companion. You get to refer to this on a test, okay? There are a few really basic formulas that are not included in there that you're supposed to memorize, but they're noted on here. The formula itself isn't on here for example, Ohm's law, but it says when we get to whatever section that is, yeah, section 4, Ohm's law isn't written there, but I wrote down that you should memorize Ohm's law. And so that you get to refer to when there's a test. And then this last one, this is, well, like it says at the top of the first page, an outline of what I'm going to be covering in class. You'll need a notebook or something to take notes on, because what I typically do is when I want to do a sample problem, for example, the question is written down in that handout that I've given you, because I figure you don't really need to take that close a look at what the question is. The thing that's important is how to get the answer, and I'm going to be writing that out line by line up here and making you write it down yourself so that you kind of stay focused on it that way instead of looking out the window or something. Oh, that's bad. First time I've turned this on in
Turn the light off, please. I'm so excited.
well, that's why you have another copy of it. Yeah. Just a second. I'll be right back.
You slept in. That's what it says.
I tried to go class. I couldn't.
Much better than any projector.
I could probably make it.
Oh, he's bringing out the second one.
It's gonna bounce right now.
I was surprised to see one of these.
Wow.
I have a spare.
Sorry, you're so totally picking on this whole situation.
And it's usually not that dim, but I didn't use that at all during the fall season.
No, you're not.
And let's see if this one's any. I haven't turned this one on for a couple of years, so yeah, that's a little more.
Much.
Yeah, I may have to check. Maybe this needs a new bulb. I'll fool with that after class. Anyhow, for those of you who maybe have a hard time seeing that, all it is what you've got in your hand anyhow. It's the note packet. I just like it on the wall, so I've got something to point at while I'm going through it, which doesn't show up on the video anyhow. Yes, I know. I get some chuckles for my Stone Age technology here. They did actually ask me a number of years ago if I wanted this room converted into a smart classroom, and I basically said, what for? The light bulbs in these things are worth $2 or $3. The light bulbs in those projectors for the smart classrooms, move the decimal over about 2 places, and that's just for the light bulb. So considering it does the same thing, I mean, I don't really use any of the smart features in the smart classrooms. Besides, they wouldn't let me keep my chalkboard. So enough on that. Most of this course deals with electricity and magnetism. There's a little bit of thermodynamics at the end. I want that about that high. How am I going to do that? Any course where I cover electricity, I like to start out with this little demonstration here. Wonder if I can. that will work a little better. So our modern words for electricity and electron and things like that come from the ancient Greek word for amber, as in that yellowish, semi-precious gem. It's basically fossilized pine tree resin. The Greeks discovered more than 2,000 years ago that if you take a piece of amber and rub it on some fur or a cloth or something like that, that after you've done this, it will pick up little bits of leaves or lint or something like that. Sort of an attractive effect, sort of like you see with a magnet, but they needed, it's two distinct things, electricity and magnetism. And so well, you know, there's this one kind of weird effect that happens with a lodestone, and they named it after, I think there's a region in Greece called Magnesia or something where they found these things. And then there's this other similar kind of thing that happens like when you rub a piece of amber, and that's where the word comes from. Well, a little bit more of a budget. I don't have amber. I've got a piece of plastic. I believe it's Bakelite. Rub it on a piece of fur a couple times. This thing hanging on the string here is traditionally called a pith ball. Pith being a sort of a cork-like substance that comes from plants. It's actually plastic coated with a little bit of graphite. But the thing to notice, and actually this is going to show up better on the video maybe because the camera's closer than you are, but after I touch the ball with the rod, they really don't like each other. Now, I have here, no, that was not what I had in mind for that. Let's charge it up again. Got a glass rod. It's actually real glass. And rub it with a piece of silk once or twice. And I don't know if you can, I should do it again out in the middle of the room somewhere, maybe, but the ball is attracted to the glass rod. It's still repelled by the plastic rod. Now it's touching that thing. I'll tell you what, if you want a closer look at it, let me invite you to play with these all you want to on your way out at the end of class. But based on these types of experiments, it was determined a long time ago that there are two types of electric charge. Okay, the terminology that grew up around this thing is that rubbing these was said to charge them. And since this attracts the ball, but this repels the ball, there's apparently two different kinds of charge. Like charges repel because the way the ball got charged was by touching this. Some of the charge jumped off of this onto that. So therefore, likes repel, opposites attract. The two kinds of charge were given the names positive and negative by Benjamin Franklin. So this kind of thing has been known about for a long time, to some extent, for more than 2,000 years, although more work was done, you know, more recently, like in the, no, not that high, like in the 16 and 1700s. A complete understanding of what you just saw, though, you know, I should do it one more time, kind of holding it up like that. Rod repels, I don't have it charged up quite as much now because I sat the thing down, but rod repels ball. Complete understanding of that is only about 100 years old because it involves the structure of the atom, which only came to be understood in the early part of the 20th century. As little children in elementary school now know, but nobody knew in the 19th century, an atom has a structure kind of like the solar system in some ways. It's sort of an oversimplified comparison, but just as you have planets orbiting around the sun, held in their orbit by gravitational attraction, in an atom, you have electrons orbiting around the nucleus, held in their orbits by electrical forces. The nucleus is positive, the electrons are negative. The outermost electrons are not bound terribly tightly to the atom. It's really easy to knock them off. This is, for one thing, pretty much what a chemistry course is about. Most of you, I think, have already taken some chemistry, and you know that they're always talking about this atom gives an electron to that atom, or this atom shares a couple of electrons with that atom, or things like that. Well, atoms can not only gain or lose electrons by chemical means, by reacting with each other, but kind of just by mechanical means. They can just simply rub off. If this piece of fur was coated with red paint, it was all soaked with red paint, and then I ran it along the rod like that, I would smear red paint all over the rod, right? Well, in a kind of a similar way, rubbing it smears electrons all over the rod. And so if both the fur and the rod start out neutral, transferring some electrons in that way makes the fur end up positive and the rod end up negative, because now it's got more electrons than it used to. When I rub the silk on the piece of glass, well, it's all just a question of which materials the electrons like better. Well, electrons don't really have personalities with preferences like that, but it's whichever material attracts them more strongly. The electrons like the piece of cloth better. The glass rod loses electrons, leaving it positive. Charging by friction is what it's usually referred to. Same sort of thing that happens if you scuff your feet across a carpet on a dry day and then sneak up behind somebody and touch their ear or some sensitive area like that, and the spark jumps and they jump. So what this was all about, I guess, was to start out the course with the question, what is electric charge? Well, electric charge is a property of elementary particles, little tiny things like protons and electrons and all those little things. They have several numbers associated with them that we've made up names for, like mass and angular momentum, and some others that you probably haven't heard of, baryon numbers and things like that. Well, one of these numbers has been given the name electric charge. And you can tell if a particle is charged because if it is, it will be attracted or repelled by other electrically charged particles. And there really isn't a better answer than that as to what charge is. It's just a property of elementary particles. Macroscopic things, like a plastic rod or somebody who's been running around on a carpet, they become charged by gaining or losing electrons. One misconception I come across sometimes, I'll put a question on a test asking somebody to explain how things get charged up, and they're like, well, let's see, this charge was negative, electrons are negative, so that must mean it gained electrons. This glass rod became positive, protons are positive, so it must have gained protons. No, I got you on that one. That's when the red pen comes out. Protons are buried down in the nucleus of an atom. The amount of energy needed to get a proton out of a nucleus is roughly 1,000,000 times as much as the energy needed to remove one of the outer electrons from the outside of an atom. So in ordinary materials, like hopefully everything you have laying around your house, the protons don't go anywhere. The only exception would be if a certain type of radioactive decay is involved. If you have a piece of radium laying around your house, then yeah, it's giving off, as the nuclei decay, a couple of the protons escape from the nucleus in the form of an alpha particle, and then you really do have a transfer of positive charge in a case like that. Actually, when I was a kid, radium was a fairly commonplace thing. You had it on clock dials. Till I was, well, I don't know how old, I slept next to an alarm clock with a radium dial on it.
It didn't actually do much damage to people, though it did a lot of damage to people who made them.
Yeah.
Most of them were young women who worked in sweatshops, and they would lick the tips of their paintbrushes to get a finer tip, and eventually their jaws would just decay and fall off of their faces.
Because radium is in the same column of the periodic table as calcium. And so if you ingest it, it becomes part of your bones.
And their body basically stored in their bones until their faces fell off.
Yep, nasty stuff.
Yes.
This is part of the story of where the Food and Drug Administration came from. I mean, today it's like, oh, you know, we got to cut back on government regulations, blah, blah, blah. Well, in the good old days before government regulations, they used to sell patent medicine where the main ingredient was radium.
Or cocaine.
Oh, that was another good example. Yeah, cocaine is a little, you've got a fighting chance with cocaine. You start drinking radium every day, you're not only going to die, you're going to die slowly and horribly.
Actually, the majority of the people who owned the radium factories would blame the young women who got sick, saying, quote unquote, we just were hiring the sick and decrepit young women to give them a chance at taking care of their families before they died. You know, in reality, they were the ones killing them. They were helping them.
Anyhow, we digress. So, a property called charge is part of the basic nature of protons and electrons. Large-scale objects become charged by gain, you're losing electrons, and I did all of that. Electric charge is measured, well, the charge on an electron is actually sort of a natural unit to measure electric charge in. But first of all, it's a really small amount of charge. And aside from that, all of this was set up many years before the electron was discovered. So the SI unit for electric charge is called a coulomb, after Charles Coulomb, whose law is a little further down the page. Whenever I've introduced a new unit last fall, I usually explained how it was related to the three base units, the meter, the kilogram, and the second. Well, that's fine as long as you're just restricting yourself to mechanics. The SI system actually has 7 base units, not just 3. And the coulomb can be thought of as one of them. Actually, the SI system has just been, as far as the basic standards it's based on, it's just gone through a revision. And that is the way it's done now. Is the coulomb can be thought of as the total amount of charge you'd have on a certain rather large number of electrons. Or actually, if you did it with electrons, that would be -1 coulomb. So maybe I should say protons, so we're talking positive numbers. Anyhow, charge on the electron is that number there, which this is not the last time you will see that number. And that's one of the things you can look up in your reference handout there. The formula sheet is not all formulas. After you flip through several pages of formulas and get toward the back, there are a number of tables where you can look up useful information. And this is back there in one of them. Electric charge is conserved. There were several quantities we saw last fall that are conserved. Energy is conserved. Linear momentum is conserved. Angular momentum is conserved. And another thing you can add to that list now is electric charge. So for example, if the fur started out neutral and the rod started out neutral, and then I transfer some electrons, the amount of charge gained by the one is equal to the amount of charge lost by the other. So the total charge between the two things when you add it up remains the same. charge is quantized. There's a word we haven't thrown around before. Something is quantized if only certain values certain special values are possible. The number of children in a family is quantized. There are no families out there with 2.78 children. It's always an integer, okay? And well, actually, it's always a positive integer, to be precise. Electrons, likewise, get transferred in whole numbers. There is no way that I would have transferred 2.78 electrons from that piece of fur onto a rod. So the charge on any object is always a whole number multiple of this basic unit of charge, 1.6 times 10 to the negative 19th. Now, when you're dealing with large amounts of charge, the fact that it's, you know, granular like that doesn't really show up. You know, if you're rubbing balloons on your hair and sticking them to the ceiling for somebody's birthday party, you've transferred a lot of electrons when you do that sort of thing. But where it shows up and becomes significant is, for example, I believe it's lab number 3 that we'll be doing in here is Millikan's oil drop experiment, which is how you measure the charge of an electron. And what you have there is you have a little chamber, you spray some very small, you know, micron-sized drops of oil into it, and as it passes through the sprayer, the little oil drops pick up or lose a small number of electrons. You measure the charge on a number of these oil drops. If you measure just one, you don't know if you've measured the charge of an electron or not, because it might have 3 units of charge or 4 units of charge. But you measure the charge on a whole bunch of them, it's always a multiple of the same fundamental unit. And you get the charge on the electron from that. Most students really hate that experiment because it's a little on the demanding side, but it's, well, that's just too bad. It's one of the really, as far as the history of the subject goes, it's quite a significant experiment. Forces between electrically charged objects. Just got to turn a page here. Coulomb's law. I'm going to avoid writing in this area here because I was looking at this morning, and that light reflects off the board and goes into the camera, and there's just a big white blob there, and you can't see anything I write. So we'll go over here. We have 2 charged objects. We're going to use the letter Q for how many coulombs of charge is on each one. This could be, for example, a hydrogen atom. This is a proton. This is an electron. Or it could be, if I went in the back and got another one of these things, I could have charged up 2 of these pith balls. There's one of them and there's the other one. I'm going to draw it with the force being repulsive. If they're both positive, or if they're both negative, they'll repel each other like that. If you've got one of each, they'll attract. Well, I had to draw it one way or the other, and I did it with it being repulsive. Separated by a distance r. R as in the radius of the electron's orbit if you're talking about a hydrogen atom, distance of the electron from the nucleus. This force is the same size as that force. This is an example of an action-reaction pair. Hopefully you remember Newton's third law, heard of that somewhere before? If object number one pushes on object number two pushes back on object number one with an equal and opposite force. So however many newtons that is, same number of newtons pushing on the other one over there. The magnitude of that force of course, is a vector. There's a magnitude and a direction. Let's take them one at a time. Probably identify all that stuff. Q is the symbol I'm using for the charge. How many coulombs? The magnitude of a vector is a positive number by definition. That's the reason for the absolute value signs. Now, Coulomb's law bears a distinct resemblance to Newton's law for gravitational forces that you hopefully remember from last fall. If this was the Earth and the Moon, the gravitational attraction between them is some number times m1, m2 over r squared. Charge is to electricity what mass is to gravity, okay? Same pattern here, some number times q1, q2 over r squared, but one difference between charge and mass is always a positive number. You're not going to find a rock with a negative mass laying around somewhere. Charge, on the other hand, can be positive or negative, so if I want to get a positive number, I stuck absolute value signs on there. R is the distance between them, as illustrated on the picture there. Epsilon 0, or its physicists often seem to like to call it epsilon naught. It's like in that one episode of Mythbusters where they had 3 different cars that they were going to perform some sort of test on. Said, well, this car is from the 80s, this car is from the 90s, and this car is from the noughties. And, 0, 0. Anyhow, epsilon naught, epsilon 0, whatever you want to call it. The official name is the permittivity of a vacuum. PERM, forgot to dot that I. Permittivity. Or permittivity of free space means the same thing. The proportionality constant in Coulomb's law is 1 over 4 pi epsilon naught. And rounding off a little bit, it's about 8.99. It's got a whole collection of units on it. Newton meters squared per coulomb squared. Actually, if you want to round it off a little more, it's really easy to remember. It's 9 times 10 to the 9th. It's actually slightly under that. Now, just like Newton's inverse square law for gravitational forces, this assumes point-like charges, and it also works for spheres. If you have a spherically symmetrical charge distribution, this works. Time to shift the camera over a little, I guess. For point charges or spheres, and I'll tack one more thing onto that. In a vacuum. The electric field exists in some material substance, glass or something like that. It has an effect on the proportionality constant. I'll briefly mention that later in the course, but that is the magnitude of the force between electrically charged objects. As for the direction, well, just keep in mind what I said earlier, that likes repel, opposites attract. I suppose that should probably have a box around it too, because that's the notation here is a little different than the textbook. The textbook puts this all together with that by writing it as a vector equation with a unit vector stuck on the end. And that's a nice compact way of putting everything together. But for a bunch of introductory students, I think it's less likely you'll get mixed up if you keep it two separate questions. Figure out how many newtons is the force. Once you've got a number in front of you, stop and figure out which way it points, rather than mixing the two questions all together in some sort of a vector statement. So that's Coulomb's law. Gives the force between point charges, like the proton and neutron in an atom, or proton and neutron, proton and electron in a hydrogen atom, or the force between a couple of little spheres like these pith balls I've got here. If you have a more complicated shape, or even, this isn't that complicated, like this charged rod here. If I had two of these things hanging from strings, it's not going to behave quite that way. Two long, thin charges like that, it's actually more like 1 over r to the first power rather than 1 over r to the second. Or as we'll see before we've gotten too much further into this, the force between dipoles, or the field of a dipole at least, is an inverse cube kind of thing. So different ways of distributing charges can create, you've got different formulas, but the point charges, Coulomb's law tells you what's going on. And anything can be thought of as point charges if you get them far enough apart. No, that's actually kind of an oversimplification. I shouldn't say that. A brief example to throw some numbers at that, and then we'll go on. So let's say I've got a couple of these little charged balls. This one's 2 coulombs, this one's 3 coulombs. One thing that you'll see in this example is that a coulomb is actually an enormous amount of charge. So let me get it written down first. Let me just move the camera over there. I need a cameraman. Okay, yeah, that'll show up. For some reason, the focus just fucked up. Oh, camera. Okay, that worked. There's the formula I'm going to throw the numbers into. I didn't bother with the absolute value signs because they're both positive numbers anyhow. Drop the numbers into that formula. Like it says over there, the Coulomb's law constant is about 8.99 times 10 to the 9th. And then we've got, for the charges, 2 coulombs and 3 coulombs. And the distance between them needs to be converted from centimeters to meters. There's that whole system about using, or that whole issue of using consistent units. The short version of the story is to say, look at the last page of the reference handout, and there's a column that says standard SI unit. And if you always, page 10, if you always use the units in that column for the numbers that you put into the formula, you will get a unit in that list out. So centimeters have to be converted to meters, minutes have to be converted to seconds, and this should all sound very familiar from previous experience. Anyhow, if you calculate that, it comes out 5.39 5.39 trillion newtons. A newton is a little bit less than 1/4 of a pound, so we're talking about a little over 8 trillion pounds of force. Like I mentioned a moment ago, a coulomb, as a static charge, a coulomb is an enormous amount of charge. I was lucky if I got a microcoulomb on this thing when I charged it up just now. Why have such a tremendously large unit to measure charge? Well, if you start talking about electric currents, like if you turn on the headlights of your car, it takes only a fraction of a second for a coulomb of charge to flow through the light bulb when you're talking about an electric current. But a static charge, where you just, rub a balloon on your hair or something like that, if you could get a whole coulomb, your head would explode. It's there, is where it is. I was comparing this to Newton's gravitation law a moment ago, but one difference between Coulomb's law and Newton's law for gravity is the size of the coupling constant here. The gravitation constant, which maybe some of you remember measuring that was one of the labs last fall, that was something times 10 to the negative 11th power. This is something times 10 to the positive 9th. The proportionality constant is 20 orders of magnitude bigger for electricity than it is for gravity. So electricity is basically a much, much stronger force than gravity. Gravity is of interest to astronomers where you've got huge amounts of mass involved. But when you start talking about small scale things, atoms and molecules, gravity doesn't matter. This is the stuff that matters. And maybe I should give you a little pep talk for why it matters to study electricity and magnetism. This is the basic force responsible for all of chemistry. Electric forces, electromagnetic forces are what hold atoms together and bind atoms into molecules. Electrical forces, of course, are also what make the lights come on when you throw the switch and make your cell phone work. And so it's also in the foundations of studying electronics. So it's kind of important. I need the direction as well as the magnitude. It asks for the force on the 3 coulombs. That's the one over on the right. Since these are like charges, they will repel. That means the one on the right is going to get pushed away from the 2 coulombs over on the other side there. So the direction of the force is to the right based on the fact that like charges repel each other. If the question had been, what is the force on the 2 coulomb charge, that would have been the same number of newtons, but the direction would have been to the left. And I've still got a couple of minutes left to introduce the idea of an electric field vector. So we have here, get this thing charged up again. We have here action at a distance. I guess the camera's actually over here. This rod exerts a force on that ball from a distance. It doesn't actually touch it. Now, I don't know about you, but I can't do that. I can't just kind of stand here and go, woo, and knock you out of your chair. If I want to exert a force on you, something has to transmit that force. I have to poke you with a 2x4 or something like that. So there is some kind of an invisible 2x4, some kind of an invisible stick or something between the rod and that ball. So this invisible something that transmits the force from here to there is called an electric field. Similar to the gravitational fields that do the same thing. You jump up in the air and the earth manages to exert a force on you without touching you. It pulls you back down, and an electric field is a similar kind of thing. So charged objects create an invisible influence around themselves called an electric field. One way to describe the strength of the field is with an electric field vector. Which, as I'll get written down in a moment here, is pretty similar to the way that a gravitational field is described. But electric field vector well, in words, it's the force per unit charge. Symbols, E for the electric field vector, F over Q, force per unit charge. I'm going to put a little T subscript on there. T for test charge. It's like, if I want to know the value of the electric field at different points around this rod, well, my test charge would be this other charge I've got on the end of the string here. If I put the charge right there, I notice how big the force on that charge is. The bigger the force, the farther it would get swung to the side. And I divide that by the amount of charge on this ball. I put it at some other point over here, I can do the same thing. How much force does it feel there? Divided by the charge of my test charge, and so on. This test charge, by convention, is positive. got to define it one way or the other. And it's sort of a coin flip arbitrary decision. But the convention that's used is that the electric field points in the direction of the force on a positive charge. The force on a negative charge would be anti-parallel to the field. And it looks like at that point, I am out of time. So we'll stop here for today. If anybody notices any problems with the recording, let me know. Like I mentioned, we can always do this in a classroom instead. And if you want to play with my toys here on the way out, if you have a minute, you're welcome to do that too.